All right, so we might ask, and these are kind of wild speculations that we're looking at here. And so how do we know this is correct? And the answer is there's some theory that predicts how these neutron stars should appear to us. And how that works is that normally what you would expect is that a neutron star would form in a binary star system because the majority of star systems are double or even triple or quadruple star systems. So if we had a nearby star that hadn't died yet, that is circling around the neutron star, let's say that this represents our neutron star. So this is just a rapidly rotating object. Why is it rotating so fast? Because like an ice skater, if she pulls in her arms, she'll start to spin faster. It's called conservation of angular momentum. And so if you have a whole star that collapses down to just the size of a city, it could be rotating 1,000 times a second. And so that's conservation of angular momentum. So we've got this very small object about the size of a typical city, 5 or 10 miles in diameter. But because it's rotating so fast, you've got charged particles moving within this thing that produce very strong magnetic fields. Now the magnetic fields tend to be off-axis from the rotational axis. And this is also true of the Earth. The Earth's north magnetic pole isn't true north. It's off a little bit maybe in our location here. You have to make a correction, I don't know, 16 degrees, 17 degrees or so to go from magnetic north to true north. And in a neutron star, we think that shift might be even more. So that the magnetic poles would be shifted by a significant amount. So here we've got the rotation of the star along this vertical axis. But the nearby star is going to start dumping matter down the neutron star because the neutron star has such strong gravity forces, it just basically suck it in. Okay? And so these particles then will do much like what the aurora did on the Earth. They will generate huge amounts of energy as these particles spiral in toward the north and the south magnetic poles. But instead of producing aurora, what these things do is they make big jets, okay, because the energies are so much higher. You've got these particles spiraling in, and each time that a particle is spiraling, it produces electromagnetic waves. And so what we expect then is a giant jet of energy to shoot off from these particles that spiral inward. So they produce jets of energy. And so those jets shoot off from the north magnetic pole and the south magnetic pole like this. While the neutron star is rotating around like this, the jets are sweeping out what we could think of as being like a lighthouse beacon. And so it sweeps around like this. As the star rotates like that, the jets are sweeping around like this, both above and below. And so let's say here's the Earth, and here's the neutron star, here's the jet pattern. But then as the jet sweeps around to this position, one time per cycle, the jet can pass by the Earth. Like this. Okay, and so it's rotating round and round like this. So what the Earth sees then is a series of pulses. So this is called a pulsar. And so if the Earth is in the right alignment with this neutron star, where here's the rotational axis, And here's the conical shape to the jet pattern as it sweeps around. What the Earth will see is the neutron star apparently producing pulses of light. So if we plot the pulses versus time, it would be regular, like this. If the neutron star is rotating once per second, then this would be a 1 second period. If we were doing it 1,000 times a second, then this would be 1 millisecond period. And so here's some pictures then of those kinds of pulses. And this was a big mystery to scientists when they first started detecting these pulses, because they thought that these were signals from an extraterrestrial intelligence. And they called these signals the LGM signals, for little green men. But then as they started thinking about it more, they realized that it's too regular and that there's no information content in these signals. And so they started looking for a more natural explanation. And this idea of the rapidly rotating neutron star producing jets of energy. And those jets then just sweep past the Earth 1 time per revolution. So imagine then you have a lighthouse. This is just like a lighthouse. So the lighthouse is always on, but when the lighthouse, as it turns around and points toward you, you see a flash. And then the lighthouse is pointing somewhere else, so you don't see the flash again until the lighthouse is pointed at you. You see a flash again. So that's what we're seeing. It's always on. So it's not really producing pulses of radiation. It's just we're seeing the continuous radiation as that lighthouse beacon sweeps past our eyes 1 time per cycle. And so this is the evidence then in favor of the idea that neutron stars exist. Now something like 1,000 years ago, there was a supernova explosion that was measured by the Chinese and also by the Anasazi Indians and the antecedents of the Hopi in western U.S., somewhere around Colorado, New Mexico area. And this supernova explosion was so bright that it was clearly visible in the daytime for about 3 days. And you could read by it at night. And the Chinese and the Anasazi were able to identify the location of this thing with respect to other constellations that were nearby that verified that they were looking at the same thing at the same time. And so now, when we look in that same part of the sky, this is what we see. This is called the Crab Nebula here. The Crab Nebula, which we're looking at a more magnified portion of it here. This Crab Nebula is the supernova blast pattern from an explosion that happened 1,000 years ago. And what we find, guess what? When we look in the center of this thing, is we find a pulsar. And so the pulsar is producing those blips of light, and we have the verification from the ancient astronomers from 1,000 years ago that this was a supernova that was there, that is now the expansion of the material has taken this shape over 1,000 years, and we found the pulsar at the center. And so this is all that fits into a pretty good theory for what happens to stars that produce the kind of elements that make life possible for us in our solar system. Okay, so that's case 2 then. That deals with the neutron star and the supernova that is associated with it. But what about case 3? Well, in case 3, we basically have the same thing that we had in case 2, all the way up to the formation of the iron core. So in case 3, the mass is greater than 3 times the mass of the Sun, rather than being between 1.4 and 3 times the mass of the Sun. Remember, that was case 2. The mass is less than 3 times the mass of the Sun, greater than 1.4 mass of the Sun. That gave rise to the neutron star / pulsar and the supernova. Case 1 was when the mass of the carbon core was less than 1.4 times the mass of the Sun. That gave rise to the white dwarf. Remember, the white dwarf is held up by electron forces. The neutron star is held up by neutron forces. But what holds up the star's weight if it gets to be greater than 3 times the mass of the Sun? The answer is nothing. The iron core collapses to 0 size. So we still get the formation of the iron core just like in case 2. But now if we just start from the iron core, it doesn't stop at the size of a neutron star, but it collapses to 0 size. Which seems very, very strange, but that's what black holes are all about. So this becomes a stellar-sized black hole. So basically then a black hole is a star that has been smashed to 0 size. And so is it really 0? Or is it just so small that we can't measure its size anymore? Well, probably it's just so small that size doesn't have any meaning anymore. So how small is this? We think somewhere on the order of 10 to the minus 35 meters, which is also called the Planck length. We think black holes are on the order of about this big. So how big is that? Well, it's as much smaller than a bacterium as a bacterium is smaller than the galaxy. And so it's unmeasurably small. And there are reasons to believe that you can't get any smaller than this and still have a reasonable definition for size. And so this has to do with some quantum physics and the uncertainty principle. And it turns out that our reality actually gets a little fuzzy on these smaller time scales and also on these smaller length scales. And so associated with this, there'd also be a fundamental unit of length, or of time, too. That would be around 10 to the minus 43 seconds. That would be the fundamental unit of time, called the Planck time. So we're not sure about all of these things, but some people don't like the idea that the black hole could actually not be taking up any space at all. And we could say here that it's so small that it would be unmeasurably small. It might as well be 0 size, even if it isn't quite 0 size. And so why is it so small? Well, because no known force in the universe can stop its collapse. So we go back here, we see that at sizes around the size of the Earth, electron forces can stop the collapse. That's all you need for these smaller sized dead star remnants. For a neutron star, it's the neutron forces that stop the collapse. But for a black hole, no known force can stop the collapse when the mass gets this big. And so this is creating more gravity, more concentration of gravity than any other known force in the universe. Now, does that mean that this is the end of the story and that we won't eventually find that black holes actually take up a little bit of space in some really strange condensed form of matter that we don't know anything about? That's still possible. But at least according to conventional theory, we consider the black hole to be essentially zero in size. And so this makes it one of the weirdest objects, regardless of some of those details, which we haven't totally got ironed out yet. This makes a black hole one of the weirdest things that has ever appeared in science. And so if we look for a moment at the structure of a black hole, by the way, as we're going through these, I should show you a few of these neutron star blast patterns. Those are pretty cool there. That one is caused by a strong magnetic field directing the blast out along a polar axis. So there's some really interesting kinds of blast patterns from neutron stars. Oh, and here is a explosion that happened from a neutron star back in 1988. This was observed in the Large Magellanic Cloud, which is a dwarf galaxy that is being devoured by our Milky Way. Turns out that our galaxy is a cannibal. It eats other galaxies, and so it's in the process of eating the Large Magellanic Cloud as we speak. But this supernova didn't take place back in 1987, it says there, 1987. It happened something like 75,000 years ago. And we're just seeing the light that came from back in 1987. So here are a few more of these pictures of, these are again the remnants of supernova explosions. There's in the Crab Nebula. That's kind of cool. You can see there was a big explosion there and gives rise to that big nebular pattern. But then here's our black hole. Okay, so this is case 3 now. And so it's interesting then to look at the structure of a black hole from the standpoint of our known laws of physics. And so the cross-sectional view of a black hole involves a central point that we call the singularity. And so this is where all of the mass of the black hole is concentrated. So that's that point of infinite density and zero size. And so you'd say, well, what else could there be? If the object crashed down, then the cross-section would only involve something that was a point and wouldn't have any other structure to it. But there's still the effect that it has on the external universe. So that gives rise to what's called an event horizon. And so this is sometimes referred to as the size of a black hole, even though the black hole that can be a little confusing, because if the singularity where all the mass is concentrated has no size, then how can you talk about how that's a really big black hole? You know, that just sounds like a conflict in terms. But no, because you can still talk about the zone of darkness. So this is the size of the zone of darkness that surrounds the black hole. Now, why is there a zone of darkness? Well, the reason why is that at a certain point, the escape velocity is greater than the speed of light. So if I throw this pin up in the air, it doesn't escape. It comes back because I haven't given it escape velocity. But if I throw it up with an initial velocity of 11 miles a second, it'll completely escape the Earth's gravity and keep going. Okay? And so here, we can think of this as being a line such that if you cross that line, the escape velocity is greater than the speed of light, which means that not even light can escape. And that's why it's a zone of darkness. And since nothing can travel faster than light, this means that nothing can escape, not even light. So at this point then, at the edge of the event horizon, escape velocity is greater than the speed of light. So you cross that line, nothing can escape. Not even light. So the zone of darkness then that surrounds a black hole is defined by the radius of the event horizon. And so how big is the event horizon? Well, the radius of the event horizon is about 3 kilometers, which is about 2 miles, for every solar mass in the black hole. So you can have some really big black holes, as it turns out, at the centers of galaxies that have billions of times the mass of the sun. So if you multiply that by 3 kilometers per solar mass, you get billions of kilometers distance. And so you can actually get a black hole at the center of a galaxy that is maybe the distance from the Earth to the sun. That's how big these black holes can be that are in the centers of galaxies. But the regular stellar-sized black holes that we've been talking about so far only have a few miles diameter for the radius of the event horizon. But if you dare to cross that line, you step across, you'll never get back. Okay? Because Einstein has predicted, and this has been verified over and over again, that this is the speed limit for how fast objects can go in our universe. And so you can't go faster than the speed of light. And even light can't go faster than the speed of light. It always goes the speed of light. And so if the escape velocity is greater than the speed of light, no material particle can escape and no light can escape. And so it just becomes a big, huge zone of darkness and something to avoid.